I guess Ankur is also here for any questions.
Oh, you changed the order.
It's alphabetical, I guess. That's why.
Yeah.
You did that. Okay. Good. So this is just a continuation of just how do transformers work. So for this part, I want to try to explain a little bit about what this basic architecture of self-attention, compositions of these things, what they can do in a very simple example called the induction heads. And then I will move on to talking about some theoretical perspectives that people in the field have started to take and say things about transformers. Okay, and yeah, feel free to interrupt me anytime. Okay, so just to remind you from part one, what the transformer. So again, we're thinking about this sequence-to-sequence mapping, where you map a sequence of tokens or a sequence of words into a sequence of vectors, and the hope is that the sequence of vectors at the final at the end somehow captures some semantic information about the sequence of tokens. Okay, just for terminology's sake. Maybe this came up before, but usually you think of this input sequence as the prompt that you type into ChatGPT, and then you hope that the transformer does something with that sequence of tokens. So that's the prompt in this context. Okay, so this was a transformer. It transforms the sequence of tokens layer by layer into a sequence of vectors. And there's a bunch of intermediate layers of vector sequences. And kind of at the heart of a transformer, when you zoom into one of the components, is this so-called self-attention head. And this is just describing, again, what Ankur told you, how a particular word in your, element of your input sequence gets transformed into a new vector. And it's done using this so-called attention mechanism. So this word here will have, have some word embedding associated with it, some vector representation. Maybe also has some information about what position it is in the sequence. Maybe this is at the very end of the sequence. And the new vector that you generate from that will be some weighted average of the kind of values for all the other words in your input. And the weights that you assign to the weights that you use to do this weighted average depends again on some vector representations of these words in the input. Okay? And this was given by these the query representation for this word and the keys representation for all the other words in the sequence with some transformation, this softmax transformation, and these determine the weights, these alpha t's, for combining the values associated with all the words into your output. Any questions about just again this kind of basic operation in the self-attention? Let's say this is the entire context or the entire length of the prompt. I think I often will use n for that. Yeah. In this case, since this is at the end, everything's a previous word. But yeah, this is an issue with like whether or not you are doing this masking or not masking. Let's not worry about that for now. But yeah, maybe in like what's called the decoder part of a version of a transformer, you would even Brown would only look at the quick Brown. Yeah. Yeah, Q sub like the dog, the vector you got from the word embedding, maybe plus this position information, and then that got multiplied by this query matrix, and that you got this Q vector. Has position information and also some semantics about this word dog. Okay, so there's two parts here, the first part and the second part. The first part, you can think of, what values goes from this layer to the next layer. And these are determined by the value vectors associated with all the tokens of the input. And so, that's one kind of part of a self-attention mechanism. And then the other part is just sort of which words do you look at? How do you do the combination? So it's useful to think about these two different parts of a self-attention mechanism. What information do you pass up, and where do you look for this information in the sentence? Okay. So I want to say a little bit about the second thing first. These are what people call the attention pattern in the self-attention operation, and it's useful to think of sort of two modes in which self-attention will be operating. One is that maybe your query for a given word will kind of align well or attend to the words or the keys for just a few other words in the sentence, okay, in the prompt. And this would result in some kind of sparse weighted average of the values. And then naturally, the other possibility is that maybe the query kind of only aligns or equally aligns or misaligned with all of the words in the sentence, all the previous keys in the sentence, and this would result in some kind of like dense or uniform average of the previous values. So let me show you, how these kinds of attention patterns might arise. Okay. So the first kind of pattern, I think Encore's kind of in passing mention, one thing that might happen is that the query for, let's say, the nth word will only really attend to kind of the output will only kind of be based on the previous word. Okay. So how might this happen? This is the case where perhaps kind of remember the input vectors are a combination of both the word embeddings and the positional embeddings. So this kind of stores semantics about the words, and this part stores where in the sentence does the word appear. So in this case, perhaps what could happen is that basically ignore the word embeddings, and you only look at the relative positions or the absolute positions of the words in the sequence, and maybe the query vector for the nth, whatever happens to be in the nth position, will align well with just the key for the n-1 position. That's a case where you would see this kind of attention pattern where you're always kind of looking back just one position in the sentence. So this doesn't say anything about what values get passed up, but just what the attention pattern would look like. Okay, another one will be based on the semantics potentially, and this is something that was kind of identified in this kind of mechanistic study of self-attention or transformers in this blog post by Elhudge and et al. In 2021. And what they identified is that it seems like certain tokens will align well with other tokens. Okay. So in this case, this is maybe like the text is maybe some LaTeX you're writing in math mode, and this is the backslash, and it seems to align well with the token, the kind of the key for this left token. And why might that happen? It's because this particular pair of words is predictive of what the next word will be. Because the fact that you're writing a backslash suggests that you're going to start doing some math and or start entering some LaTeX command. And the fact that you've used left before maybe suggests that you want to write /\right. Okay, this may be predictive about what the token that the next token would be right.
In this case, does the query correspond to like the query matrix?
This is a particular query vector that you got after multiplying the word embedding by the query matrix.
Okay, and in this case, the original word was just the
backslash. Yeah. So you have the word embedding for backslash. You map it to a query vector, which is just by multiplying by query matrix. So that's the query vector for this token, and maybe it aligns well with the key vector for this token. And the reason that might occur is because this particular, what's called a skipgram, is kind of like a bigram, but there might be stuff in between. This particular bigram or skipgram is perhaps kind of reasonably predictive of what the next token would be. And if you played with what's the thing, the code version of GPT that's built into your Copilot, yeah. If you played with Copilot, it kind of always knows that when you write backslash and you have a left there, you probably want to do right next. Okay, so this is kind of a semantic kind of pattern that you see in the attention patterns. And then finally, I said that sometimes you have this kind of broad attention, kind of uniform looking attention patterns. And this tend to be associated with certain tokens, maybe also specific to where it occurs in the sentence. So if you've kind of written a sentence and you end it with a period, maybe what might happen is that you have a very kind of broad attention or uniform attention, kind of aggregates information of all of the words in the sentence. Now, one thing you might be worried about is that somehow all the information about the entire sentence somehow just immediately gets moved into this nth position. But somehow this is not always going to be possible if the size of the embeddings are not too large. So maybe like the dimension, like Encore said, not arbitrarily large, not as large as the entire vocabulary or the number of possible tokens, but something reasonably small, and like the size, maybe like the numerical precision is limited. So you can't capture everything about the entire sentence, but it's just going to aggregate information that's relevant for whatever it's trying to do. Okay, so these attention patterns can kind of tell you how information across the different tokens in your sentence or your prompt might move around from one layer to the next, but it doesn't tell you kind of what information gets passed on. And so to illustrate that, a particular functionality of transformers, I want to move on to this next example, which is kind of what introduced this so-called induction head. Any questions so far? This is hopefully just illustration of what the self-attention was doing. Okay, so the induction heads some kind of functionality that researchers, especially in these two blog posts out of the research team at Anthropic, they identified as some kind of very important sub-functionality that they discovered in some pre-trained language models. So this is an example that they give in their blog post. So this is this potential prompt that you might input into your to your transformer, and this is just the first several lines of Harry Potter after some tokenization. So maybe it broke up some of the words, like privet got broken up into 2 tokens. But this is really literally just Harry Potter, and you want to predict what the next token that will follow this snippet so far. And the way you would do that, like as a human, is to, well, okay, I don't know anything about Harry Potter, but Durs here is the last token, and maybe what should follow, I should just look back at the last time this token Durs occurred, okay, and I see it did occur before, and then I'll just predict whatever followed it. Okay, so that's what an induction head is. So again, this kind of something that was identified in this kind of mechanistic interpretability study, and it's really just an abstraction of what this kind of subcircuits people identified in these large language models, the pre-trained language models, are doing kind of throughout the transformer. Yeah.
Question. Sorry, again, terminology. Is this related to the attention head anywhere?
We'll see very soon. Yeah, exactly how this gets implemented with self-attention heads. For now, it's just some functionality that some parts of the transformer seems to be doing.
Okay. Is there anything in particular that the head refers to, like an element of the architecture?
Yeah. So head, like a weird term, just means like a unit in the network.
Oh, okay.
I don't know why it's called a head. Because multi-headed monsters or something. Yeah, that's a good question. This is some terminology thing. Okay, so the way you might abstract out what an induction head is doing is that you have some input sequence, and put some particular position in that sequence. What should you output next? Well, the induction has that, well, maybe I don't know what should follow this token, but if I just look back at the rest of the sequence, maybe I saw this token before, and I'll just output whatever came next. Maybe if you see it many times, you should output some kind of average of what came next. Let's just go with just look for the latest time you saw it and output whatever came next. Okay, so this is at this point, almost like a fully specified computational problem. You have a sequence of elements, and we have a particular computational model, which is that of self-attention, compositions of self-attention, things like this. Gonna ask, how could you implement this thing in this computational model? Okay, so here, So it turns out that you can't do this just with a single self-attention head, and you really do have to compose two of them together. Okay, so let's see how that's done. So what's going to happen? So this is our input to the self-attention head. It's maybe some vector representations of these tokens A, B, and A. Okay. And in the first thing that you might do is to somehow move information just one position ahead. Okay. So what information would be useful to move one position ahead? It turns out you want to move the key for something in the previous position to the current position. Okay. So we're going to move the key for this A token to in the next layer so that the key is now kind of sitting in the next position. But so B here is what the value in this can have the value in a query for B, that gets retained. And that's done through something that Ankur didn't talk about, which is called a skip connection. Let's just assume that you're always allowed to pass information straight through. Okay. But what you would do is that you kind of design a self-attention head that will just look back one position, copy the key, and move it to your current position. So that's the first layer. And this requires maybe some extra thing called a skip connection. Let's just assume that's okay. And now we're in a good position to solve this self-induction head task, because now the information about the previous token is now kind of embedded in the information in the current position for every token in the sequence. Okay. And now the second layer just has to kind of do the query key match. So we want to look at the query for our current token, which is the query for this token A. And now it needs to match the keys for some previous tokens. And the one it's going to match with is the one here. Okay, not the one in position J, but in the position J plus 1. Okay, because now this position has the key token for A. Okay, so we'll match the query for A here. Okay. And now when you kind of attend just to this position, you will know that the value should be whatever the value is for B. And that's what we'll output in this position. Kind of two parts to this, two steps to this implementation. Okay, you couldn't easily do it just with one self-attention head, but it really required kind of this two-step process. In some sense, yeah, you can prove something like this, that this is the same way that like a linear threshold function can't do XOR. You need two layers. Do something like this here. Two steps, which is composition of two self-attention heads.
You still have here in this construction one head in each layer.
There's two layers, right? The first one does this, and the second one does this. The first thing, kind of intuitively, you need to move information from one previous token to the current token.
Each layer here has a single head.
Yeah.
So if I think just a good architecture, it's still a single head. I mean,
but two different heads. The first. No. So the second one is just doing this matching.
What does it mean to have the same head in different layers?
It's not the same head. It's two different heads. Two different self.
You need to have different heads as opposed to the same head. And I'm a bit confused with what does it mean to have the same head in different layers?
Oh, okay. I wasn't even thinking about that. I think Nati's asking, like, would it make sense to just iterate one head over and over? Yeah, I was not trying to convey that. Yeah.
I'm just trying to understand why you're calling this two heads.
There's two. One here, one here. They implement two different functionalities, right? One is this kind of copying functionality.
Is there such a thing as a two-layer single-headed attention? A two-layer single-headed network?
Like one head in each layer. Yeah.
But isn't that what you have here?
Yeah, that is what. Yeah. but there's two different things. I don't. What's the?
I love it. Never mind. Never mind.
Okay. We'll talk later. Okay. I don't. Yeah. If you want to call it one head, that's fine too. But there's two different steps. Is that clear? Okay. So there's some detail about like if you want just the most recent match as opposed to all of the matches. Maybe that can be done by using positional information that will just bias you towards the most recent match.
So when you say A comma B, you mean A concatenated with B, is that right?
Here it's kind of a strength notation, not I don't necessarily mean concatenation. I just mean that in this position, it has the key for this token A and the query and value for for B.
The information somehow there, maybe they're added, maybe there's some other.
Somehow, yes, with some vector space magic, we could do that. Yeah.
This is like presented in the context where you have A, B, and then A, but would this work just as well if you had like A at position I and then some similar token previously?
Yeah. Okay. Good. So maybe it wouldn't be exactly the same match, but just like semantically the same match. Yeah, we'll get to that. But yeah, it could be that as well.
And like if you had like more layers now, is it more like, can I think of this because it's taking like more and more like hops?
Okay. We'll get back to that. We'll talk about that very soon. Okay. Good. Any other questions? And so hopefully this, it's a very kind of basic functionality and it turned out to be, what was identified as something very important for something called in-context learning. So who's heard of in-context learning? Okay, so hopefully if I don't understand this slide, you kind of will get the meaning anyway. So somehow in-context learning is the idea that you can just kind of put information into the prompt and have a language model kind of do some kind of statistical inference or logical inference just based on the information in the prompt. Okay. So here the example is that you give a bunch of sentences and whether this, I guess the sentiment is positive or neutral or negative, and then you have like finally another sentence whose sentiment you want to kind of predict or infer. And here, if you feed this to the language model, it will say, well, okay, this is what you mean by sentiment. I will guess that this sentence here is positive sentiment. Okay. And the idea is that this is a very flexible way of using a language model, because if you just had changed, what you meant by not sentiment now, but now the topic of the sentence, you change the labels in your prompt to what the topic of the sentence is, it would output now the topic instead of the sentiment of this last sentence. Okay, so that's just kind of at a very high level, but everyone knows already what in-context learning is supposed to be about. So you could imagine that kind of in-context learning can be enabled using these induction heads. And this is really what these research teams at Anthropic were trying to argue, that without the form kind of appearance of these induction heads in the transformers, in-context learning would not be possible. Okay. So here's a very, very simple distillation of a very simple version of what induction heads might be doing. Sorry, I mean what an example of in-context learning, like a very, very basic in-context learning problem. So this is the prompt that the text that you give to the language model or the transformer. So you just start saying things like the mother of Charlotte Eve, the mother of John is Helen, just say like 100 more of these things. And at the very end, you ask, who is John's mother? Okay. How might this be processed by a transformer? Well, maybe several layers of the transformer will be moving information around until finally, there's some sequence that just has information about Charlotte, Eve, other mother-child relations, John, Helen, and then finally we know that we want to ask something about John. So this might require many layers of a transformer, and then finally an induction head would be invoked to just do 2 more layers to kind of look back at the last time you saw John, and then predict what came next, which is Helen. It's a very primitive form of in-context learning. Okay.
Right to left or something in order to.
Yeah, so maybe that's the case where you wouldn't want to use this. You want like a forward-looking induction head as opposed to a backwards-looking induction heads. Yeah, maybe a different functionality would solve that problem.
If you had like mixed in with these statements, you had like X is Y's father as well. So like someone's name would appear with their father and their mother. Then like in theory, an induction head could be able to distinguish between that, right?
Yeah, maybe it might be much harder, and depends on what kind of happened before it got to this stage where induction head would be useful. But we'll see, like a variant of that in the next slide.
Okay.
Other questions?
So induction kind of a purely theoretical thing.
It's just an abstraction of what this team found the various parts of a transformer to be doing. And the exact details of how I defined it, can be changed a bit, but it's kind of this inherent two-step process of move information so that the next layer can just do this query to predict the next or predict some next token.
They actually identify the two-step process inside.
Yeah.
Or they just conjecture.
So clearly it's not exactly. Clearly, I can't exactly just be doing this because, like Ankur said, these are very fuzzy. Maybe it's doing a little bit more than just this. Like the vectors are not perfectly snapping to the way that you would want for this to happen. But this is one possible implementation, and we can argue about whether you could do it in one layer or 2 layers. It seems like you do need 2 layers for this.
So when you say possible, they identify this implementation inside the transformer, right?
They've identified this functionality and exactly what happens in the two layers. Maybe it's not as clean of a separation as this, and maybe it's not only doing this. Maybe it's doing other things. Other information gets passed around. Yeah.
So can't you think of this as moving the previous position's query to the following position's key?
I would think of it as you want the key of this one to move up here, so that your query.
Yeah, but the query of A should match the
Key of this one. Yeah.
You want the query of A back there to move to the key of the next one.
You want the key to move here. Yeah. Maybe it's just a matter of terminology, but you're going to make the query that you're going to ask to output this thing is based on what's here. You want the key here to move here.
This is like an abstraction for some fuzzy concatenation operation that the head is doing. Then going back to the question of like word order, wouldn't a head be equally able to like concatenate AB or BA and then interpret subsequently? Like, shouldn't word order not matter terribly? Like a head doesn't really care if you say John is the son of Helen or Helen is the mother of John.
So the information moved one way or the other, and I guess query and key relationship is not necessarily symmetric. This is why I guess Umesh's question is kind of important, whether if the key got moved or the query got moved.
This we don't understand. Why the second layer is using tags, but two left as well?
I'm not defining exactly what this notation means, but it's just that I want the value now from this position, which would be to move up here. Don't worry about it. There's no semantics except that this is supposed to represent the token A, B, and A. This one should be the token B.
Sorry. Would this necessarily imply that the same thing is happening for the other tokens? Like, is it also being carried diagonally to the token?
Yeah. So if you kind of take this literally, the output for this one, the way you would compute this output using an induction head, this behavior, it would look for the last time you saw B, maybe somewhere over here, and just output whatever came next. Maybe it was C, so you get a C here.
Okay, so it's not like it's learning it for A specifically.
I'm just giving an example for this particular position.
Okay, got it.
This could potentially happen in parallel for all the positions. To resolve the key thing. Okay, so good. So going back to in-context learning, this is a very, very primitive example of what it might mean to do in-context learning. You have a bunch of input-output pairs given in the prompt, and you just want to compute the value, the output for this corresponding input. That's basically just like a function lookup, okay? But maybe more sophisticated versions of this that don't just match exactly the tokens, but match like the semantics of the tokens. That could be seen as a form of learning or meta-learning. If you prefer just nearest neighbor prediction, or maybe other kinds of processing that happens here. And there's a very nice paper that Serbi and her research group have been viewing this as a form of doing n-gram, implementing an n-gram model. I think Tang Yu will talk a lot more about in-context learning this afternoon. Okay, so this is one thing that this kind of two-layer sub-circuit of a transformer can do, just doing in-context learning, this very basic form of it. But what kind of goes beyond in-context learning, what seems to kind of go beyond what just this induction heads can do, and that's function composition. This is something that I learned about from Binghui and Christos and their co-author. So what is the input, the harder challenge for this induction transformer to do? Suppose this is the prompt now. I guess one of the questions. Suppose I now, don't just give you, a particular function, but I kind of describe to you two different functions. So the first several sentences in this prompt is Jane is a teacher, Helen's a doctor. I just start enumerating everyone's profession. And then I follow it with, who's the mother, who, okay, a bunch of these things. And then I finally ask kind of a harder question, what's the profession of John's mother? So this is really a composition of the kind of profession of and mother of function that's given to you in the prompt. This seems to go beyond what a simple induction can do. You really need some kind of iterated form of induction head to do this. These are kind of very basic primitives of what a transformer might be, kinds of computations that what a transformer might be doing in order for it to perform things like in context learning, kind of do really, really basic reasoning over your input. Okay. Any questions about this example?
For an iterated induction head, does that mean that the single head can learn that functional composition process? You mean multiple heads?
So a single head might not be able to do it, or depending on what Nati calls one head, but maybe you can't just do this with two layers, kind of a two-step process, but you might need more than two steps.
Okay. Thank you.
So actually related to that in these papers, so here, does the depth of the network have to be linear with the number of composition steps, or?
So I don't know exactly what happens when you train a transformer to try to do this. Yeah, but representationally, and if you train it specifically just to do this, it seems to be logarithmic in the number of functions you want to compose.
No, I mean number of composition steps.
Yeah. Like I have k different functions. This is what Ramya was asking. If you have k different functions, I want to compose them all. Seems like you need just logarithmic in k number of layers.
Is there any intuition for that? Is there any intuition behind that result? I think that's a theorem.
Yeah, that's a theorem that we proved together with Clayton and Matthews. So the intuition is that every layer kind of lets you look back one step, and so the reach then will double with every new layer.
But if you have a k depth composition, can you do that with log? Can you still do that with log k layers?
What do you mean by k depth? Like k functions you want to compose?
Well, I don't know what you mean by different functions, right? But if I have x, a1 is a2, a2 is a3, a3 is a4, all the way to ak, right? So there's like k things I'm composing. You can do.
That's a log k step thing. Yeah. Somehow like the reach that you have after every layer is kind of doubles with every layer.
So these are not just functions; these are bijections. Is that what it is? It's just your associative.
Yeah. Yeah.
So because it's iterative induction head, it's 2 layers, it's just gonna iterate it with the 2-layer with the learning, like how it's still like it's 1 layer, 2 layers, 3 layers, or it can be single-headed.
Yeah, so even just for the basic induction head, it seems like there are 2 distinct steps, and this seems to require 2 different layers. One induction head for the first layer, one self-attention head for the first layer, and a different self-attention head for the second layer.
There is a paper claim that a single layer transformer that have a long enough blocking network is Turing complete.
Okay, good.
So I guess there are other mechanisms that can have the same behavior as the the stack of many composition layers. So how do you know in practice the transformer use which mechanism?
Yeah, that's a great question. So, in some sense, with just one self-attention head, you could potentially just aggregate all the information across the entire sequence into a single position, and then some kind of feed-forward neural net universality, something, something. Let's say you could do whatever you want with that. This is assuming, though, that yeah, exactly like you said, like maybe like the size of the embedding is huge, right? It grows with the length of the sentence.
So is there any experiment show that induction there is exactly how transformers do this?
Yeah, so that's definitely what the studies do. They find that this only emerges when you have two layers of a transformer, and it's because they're not using embeddings that are like as long as the context.
Okay.
Any more questions about induction heads? I think this is kind of a interesting research direction, which is to identify what are the key primitives of large language models that are needed to do these various tasks that they are purported to be able to do. How do you put them together to get more expressive functionality? This, I think, we're just kind of scratching the surface so far with induction heads.
Maybe if I could just answer this. So these are this is function composition where you've essentially given the function in full form. You've laid it out.
Exactly.
The truth table has been given. Now, if I presented a function in a little more implicit fashion, I say, John's mother is one of the following candidates, and I give you some simple rules about that. Now, that composition, as you start composing that information, it's more complicated.
Yeah.
You can't represent it necessarily as an explicit list of the same length. What would happen?
Not clear to me. Yeah, I assume that even in this very basic example, some processing had to happen before it got into like a reasonable form that just this basic induction head mechanism was useful. But yeah, you're absolutely right. Like, if you express things in natural language, you're not going to express things so regular as this. Okay. Good. So that's all I really wanted to say about these kind of what can transformers do, what kinds of functionalities they can implement. I've just described to you something really, really basic. This maybe like slightly beyond that really basic thing. And I think we just don't really understand, more complicated things at this point. So that's kind of a nice future direction. Okay, but I want to move on, if there aren't any more questions, and just talk about some other theoretical perspectives on transformers that other researchers in the field have kind of taken to say something about these things. Okay, I kind of divided into 3 or 4 parts. One is just kind of viewing things as a model of computation and just using this kind of complexity theoretic view to understand what transformers can and cannot do. The second one is about learning, just from kind of classical learning theory. What can we start saying about transformers? Are they learnable? Are they not learnable? And can we change the model of learning to say some interesting things? This will be related to something about the 2 different uses of a language model, prediction and generation. And then finally, I'll kind of conclude with some kind of precursor of transformers and something that people have been studying for a long time and trying to connect to transformers recently. Okay, so and if you write down, in full detail, in gory detail with the pseudocode or with kind of some explicit mathematical expression, you would eventually just see it as some kind of computational model, maybe even just like circuit. And if you kind of take that seriously, the same way that you think of a neural network, with softmax or logistic activation, the sigmoid activation, this is somehow boils down to some kind of threshold circuit at the end of the day. You find that this is really just some kind of class of circuits, and you can start asking, which circuit classes are contained in, which ones does it contain, and so on and so forth. And so this, has been a productive perspective to take in a number of works over the recent few years. And so maybe one kind of takeaway, this is not necessarily the most important result of this line of work, but one thing that people have been able to say is that if you look at just constant number of layers of transformers, and the size, overall size in some sense, is some polynomial in the sequence length that you want to look at. This can all be simulated by these kind of class of threshold circuits, constant depth threshold circuits. And whether it's uniform or not, that's some detail here, I guess, is important. But there are a number of implications that you would standardly take when you have these kinds of complexity or circuit complexity theoretic statements. For instance, you might be able to deduce that you cannot simulate finite automata or all finite automata unless some complexity theoretic assumption is violated. Okay. Like the number of layers is not growing with the length of the sequence. Like produce the circuit and I don't actually know this stuff, so don't ask me questions about this. Okay, so that's one model, one approach that you can take when you kind of view this seriously. It's just a formal model of computation. And another thing people have done is try to kind of take a kind of simplified version of transformers, by putting some practical or maybe like easier to think about restrictions on what the transformer is doing. And one way people have done that is, well, the softmax thing seems complicated. We don't like this exponential transformation. Let's just ignore exactly that this is a special softmax and just replace it with the max, the argmax instead. Or instead of doing the masking in a particular way, let's simplify how the masking actually works. And when you do this, you can start saying more and more precise statements. I won't tell you exactly what those are, but this in some sense does limit the expressivity of transformers. And then kind of in the opposite direction, you can kind of say that maybe some aspects of what a transformer is doing is not so important, like maybe like the feed-forward network parts of them is not so important. Let's just ignore that and just focus all of our research efforts on understanding, the nature of the communication, the attention patterns. Okay? Maybe this is some work that I did with Clayton Matus, that there's some relation to some massively parallel computation. And this is where you can start getting lower bounds for some of these very, very basic primitive tasks like induction heads. So there's going to be a whole workshop, I understand, on viewing transformers as a model of computation. So this is just, it's like the very basics of what that workshop might be about. I think one important question for this entire line of research, including what I've been doing, is what's like the relevant scale or abstraction for transformers as they're used in language models. This is not so clear from just this kind of study. Okay, let's move on to learning. So I think we didn't tell you how you train transformers, but definitely these things are not just like hand constructed. No one just literally programs these things for fun. You take data and you somehow train the parameters of the transformer to get to do something interesting. Okay? So here's the kind of the very, very basic way that transformers get trained in practice. And apologies to people who actually do this for a living. This is not, I don't actually know, but I think this is what happens. So basically the way they think about it is that a transformer is going to map your entire context to some vector. So maybe this is the context. Quick brown fox jumped over the lazy. That's just transformed into some vector through the transformer. Okay, so maybe I said that the transformer gives you a sequence of vectors. Maybe you just take the rightmost vector at the end of the day. And that's the vector H in this case. And then that gets passed as the input to some what's called a log linear model. This is something from statistics that just a model for kind of predicting some discrete outcomes as a function of some vector. This is some very classical thing from statistics. Okay, so now that we have a way of kind of distilling any kind of context of sequence of tokens into a vector, and we have some statistical model that will help us predict what the next word is going to be, we can try to tune the parameters of this model, that's including, so that was the parameters. It's all of the query matrices, the key matrices, the value matrices of all of the self-attention heads in your transformer, all of the feed-forward nets, all of the other parameters Ankur didn't mention, and all the parameters of the log linear model part. All of those parameters get tuned in a way to try to minimize some objective. And that objective typically is this cross-entropy objective.
Sorry, for the log linear model, are we modeling a transformer as that model or asymptotically?
Oh, this is a separate thing, perhaps. Yeah, this is
Oh,
a separate thing exterior to the transformer. That once you have a vector that represents the entire context, you have some additional statistical model for predicting next word.
what is the relationship between that statistical model and the transformer?
So the transformer is what produces this vector H.
Oh, sorry.
And this is used as like the feature vector for the log linear model.
Gotcha. Sorry. Thank you.
Okay, so so first of all, I should say this is what's called autoregressive training. There's some other version of training that I think Andre knows about. It's called like mass prediction. This is not that. So there's some other ways you could train, but this is one particular way you could train the transformer. And then one last thing that, okay, so I said, we're going to try to use this model to predict the next word as a function of all previous words in your training data. But typically you don't use all previous words because that's a lot. That's like the entire internet up to the current word. You just maybe use the last N words. And this is, this kind of objective is, has a lot of interpretations. It's like a maximum likelihood objective, trying to find the parameter with the highest likelihood. It's also related to information theory. It's kind of trying to find the model that has the smallest relative entropy of the data that you see relative to what your model is predicting. Okay, so that's learning in practice. But what like learning theory say about this? There's a very nice work by Edelman, Gold, Takade, and Zhang that does the standard kind of learning theory approach to studying, how well does this paradigm work? So the kind of question you can ask in learning theory is that if I manage to find a transformer, let's say with L layers, that has low training error, so my data has small cross entropy loss, how well will it do on new data that I haven't seen yet? And this is just like the standard generalization theory, sort of highly non-trivial to do this. So you have to kind of invoke these more advanced techniques of doing generalization theory. But the answer, when you read their paper, is that, well, probably yes. Probability meaning like with probability 1 minus delta, training and test error will be similar, as long as a lot of conditions happen. So training data, test data should be IID from the same distribution, standard. Token embeddings are not too complicated. They have some kind of small covering number, yada yada, and the training data set size is big enough. Okay.
There's low training error.
And then how well will it work on new data?
Data is the same as the training data.
On new data that you haven't seen yet.
I think, okay.
Yeah, how would the learning theory analysis be being different with compared with transformer and other traditional architecture? Like what's new in the transformer in the zero?
I think the interesting thing that's definitely not unique to transformer is that the training data set size kind of only depends logarithmically on the context length. So the more information you want to be able to use to make your next token prediction kind of only grows very mildly with that length. And this is kind of consistent with what people see in other deep learning generalization theory, where in some sense you find that intermediate layers of the network are kind of creating these kind of sparse combinations of the input. So the sparsity is important here.
Is the content of this theorem that if you have L layers of nice functions, how nice is other results? It's exponentially.
Yeah. So I think maybe it suggests that you shouldn't have too many layers, but one thing that's useful is that it can grow very kind of only grows very mildly with the context length.
Is it possible? It seems that the second assumption can test against existing embeddings. Is that true?
Can do what again?
You can test the second assumption against existing embeddings. Embeddings used in practice.
It's asking whether the nice the embeddings they're talking about are these nice functions that consistent with what we do in practice.
I guess that would be, yeah, that I don't know the answer to. Good question. I don't know exactly how nice these functions are compared to other things.
So are there qualitative differences between the bounds you get here versus like RNNs or other approaches to sequence modeling?
Sorry, do you know?
I think RNN also gets some, there's some results, some old result that shows that there's maybe logarithm. But
What?
then the
Okay.
state space piece, I guess it's different because the computation is happening universally across all the data versus there's a hidden state, so there's a hidden state size that show up. The reason you can get this is because you're sharing weight across. It's the
Okay,
same induction parameter. The softmax is kind of small.
Oh, I see.
I guess the RNN also shares parameters. That's important
Yeah,
here.
so that also you can make but I'm not sure of the right references.
Is that analyzed based on the program model? Is it analyzed based on the program model? Just enumerate all the possible inputs that has a length at most and
Sorry, is this based on?
program model.
Yeah,
This is for any distribution over sequences of length n, whether generated by a simple n-gram model or something completely arbitrary.
I mean, this is a type of capacity bound for how expressive are the class of functions you can get from such compositions, right?
This is not, not really saying anything strictly more than that. Okay, so this is kind of the basic things that you can say using tools from learning theory. Of course, this doesn't say anything algorithmic. This is just that if you did manage to find a good transformer that works well on your training data, how will it work out of sample? You can also ask, can we learn these things efficiently? And there's a lot of work on that as well. So can I efficiently find a low error transformer? Maybe what's interesting is, can I do it with gradient descent? So there's a lot of work trying to study this question.
What's the most you can say about that?
What's the most you can say? That if maybe like the data is Gaussian, whatever that means for tokens, I don't know, but let's say the data is Gaussian, and the task that you want to solve is very simple, maybe it was just computed by a single self-attention head, then gradient descent will do this. Not very much. I think this is already kind of non-trivial because we don't even know really how to do this for very even beyond very simple deep neural networks, let alone L layer transformers. Okay, so that's learning. I think it's sort of at least as hard because sort of there was a slide that Encore gave where when he was composing the different self-attention heads together, actually in between every layer is a bunch of feed-forward networks, which already could be multi-layer neural networks. So it's at least as hard as that.
I mean, some of these learning results don't have the feed forward in them, I think, right? The output is just really the output of the attention.
Yeah, so that's, if you only wanted to analyze how you train like a single self-attention head without the feed-forward thing, that's absolutely right. But if you wanted to say something even slightly more complicated than that, it already seems as hard as to study deep learning training.
So when you say you efficiently find low error transformer, you mean start from scratch. But what if you had one, now you want to improve it?
Great question.
Sorry, for the training error, do we make any assumptions about like what specific error, or do we just need like convexity or something?
In this theorem, I assume any Lipschitz loss is fine. The question is what do I mean by error? I think that any kind of standard loss that you ever see in a learning theory textbook would be fine.
But I think for the optimization, it matters what loss you're studying.
That's true. I think probably squared loss is the easiest one. So whatever squared loss means for a token, that's what you use. Okay. I think it's kind of interesting to think about whether this is the right notion of generalization theory for studying language models. That's, I think, up to debate. And it's kind of borne out when you start thinking about what other things people do with large language models. So I want to talk a little bit about chain of thought and hopefully not get into too much detail, but chain of thought is this kind of strategy for providing a prompt to your language model to get it to give you better answers. Okay. So suppose you want to get the language model to answer some kind of very basic math question. Maybe what you might do is just kind of demonstrate the kinds of question you want it to answer. So here's an example of a question. Roger has 5 tennis balls. He buys 2 more, blah, blah, blah. How many does he have? The answer is 11. And then I give it the real math problem I want it to solve. Okay. So this would be the standard way of using the language model to do this. And the chain of thought kind of strategy is to say, well, okay, let me kind of explain to you how I would solve this in my example, and then ask the question I want to answer. And somehow, because the model is trying to replicate what you had done in the prompt, it will kind of output a bunch of more tokens before finally giving you the answer. And maybe people thought that, well, it's because it can kind of work out to show its work, and maybe that's a good thing. This is not necessarily, you don't necessarily have to do this. You can, in fact, just not use the strategy and just add like one more line here, like please think step by step, and then it will kind of start producing some more tokens before giving you the answer. So it seems like what's important, sometimes it's just that you get the model not just to immediately answer your question, but to kind of generate a lot of intermediate steps tokens before it answers your question. So why might that be useful? Well, kind of from like a purely computational perspective, this is more space for the transformer to perform computation. And so more space could be useful. And so this is something a lot of theoreticians have kind of tried to capitalize on. But actually, maybe like another perspective is that, maybe in the training data, if you give it this kind of information, these kind of extra work steps of how you might solve a problem, this can actually make the training better. This is very speculative, but think about, like a traditional labeled training example might just be your question and then the correct answer. But suppose in your training data, you actually had a lot of examples where you don't just immediately answer the question, but you show step by step how you should solve the problem, how you should answer the question. And maybe this is kind of more useful kind of information for learning purposes. This is something that has kind of borne out in kind of different packed learning problems. So in packed learning, there's various concept classes that we think are very hard to learn, like decision trees, DNFs, arbitrary circuits. But they become much, much easier if you kind of show it how to produce the correct answer. So an example is, if you want to learn a circuit, maybe you also tell in a training time, don't just give the label of the output of the circuit, but you tell it the values of all the intermediate gates in the circuit. This makes learning a circuit very, very easy in this case. Maybe not so extreme is that maybe you don't give the values of all the gates in the circuit, but you give some kind of restricted access to the circuit. Maybe this can be viewed as some extra information available at training time, just for the purposes of making the learning easier. I don't know if this actually is what makes transformers work and why this might be valuable, but it's at least something potentially to think about. Good. Last thing, second to last thing I want to say is just about this kind of 2 different goals of language modeling. One is prediction, trying to predict what's the next word, okay, given the context. But the other thing that we do all the time is use it to write new sentences, to write new sequences, to generate, given the context, generate new tokens after that. And there turns out to be different ways you might think something's good at prediction, and different ways that you might think something's good for generation. And this was something that was exploited in this paper by Kalai and Vempala very recently, where they showed that in some sense hallucination, your desire to avoid hallucination in a very specific sense, it's kind of at odds at your desire for having kind of accurate prediction, which is represented using calibration. Somehow, the better you are at being calibrated, the better you are at prediction, the worse you will be in terms of hallucination. I don't want to say exactly what all these things are, but there's some theorem of that form.
Do we have a definition of hallucination?
In their model, they have a very concrete definition of what hallucination means. Basically, factoids that are not true facts. Whatever that means.
The generation and hallucination are not exactly the same.
But this is potentially something you want to avoid when you're doing generation. You don't want to generate false facts or factoids.
Yeah. I'm just saying that the problem of generation without doing false facts is that.
That's not necessarily the only thing you care about is generation, but that's one thing you might care about. Yeah. That's true.
Why is it intuitively clear that the more you can predict, the more you would hallucinate?
And how to get better calibration, you need to kind of understand that, in your training data, you haven't seen all of the facts in your training data, and to kind of improve your ability to make prediction, you need to kind of assign probability mass to some false factoids. Yeah, I don't really want to get into the whole detailed model here because it's very complicated. Yeah.
What if into a knowledge graph in some way, and if the predictions go to like some connection that not exists in the knowledge graph, then it can be hallucination.
Yeah, so I think their model is something. Yeah.
It's a very simple setup. So the idea is just that you have some underlying domain of things that you could say, and some of them are facts, and the others are not. The real problem, basically the way the proof works is that you take a bunch of samples from your distribution. Some of them you're only going to observe one time. Now, what do you do with things like that? Because there are a bunch of other things that if you took a new sample, you would only observe one time. So if you just give up on those, you won't be calibrated, and that's the crucial thing. But if you're trying to be calibrated, you actually try and predict, positive mass on that, there's no way to discern which are actual things in the support versus not in the support. So that's exactly what this tension is. The hallucination is just generating facts that are not actual facts. And it's really, what do you do with these tail events that are sort of rare and you see maybe one or few times. But really, I think the trouble is that by hallucinations, people mean many different things. And this is one particular notion that's really just the rare events, but people really are trying to avoid other things that are not statistically hard to avoid, but are just practically hard to avoid. Yeah.
Basically, they're saying that these other types of hallucinations that are not kind of statistically unavoidable, maybe we should avoid them just by better architectures, better design of the language model. But there are some kind of fundamental things that you cannot avoid.
Yeah, actually, I did read this paper, and I want to make a comment. Not sure if you follow with you. My feeling is they have a different definition of calibration. They have generalized calibration. It means that you have a word model. They assume they have a word model, which is a formal model of P, and the model itself is a G. So if they say that we are calibrated, it means that G is super close to that P. So it means that the model itself is a word model. It's a word model, yeah. So in that sense, it says that it always hallucinates because the word itself have lots of the hidden mass of the, not the fact and hallucinate thing. And if the model is really close to that, it means that the model will also produce lots of things like that. So that's the feeling of.
Yeah, that's exactly, I think, what Ankur was saying. And whether that's like a good thing or a bad thing, or whether you agree, that's a.
Well, I think it makes some assumption which I don't fully agree with, but we can have a conversation on it. Sure.
Yeah. Will Adam or Santosh be here later?
I'm speaking next week, but on a different topic.
Okay, I just want to close with this. It's finally kind of a very old subject that seems to have recently been kind of revived because of the connection to transformers. And this is this idea of associative memory, which is something that Hopfield was studying way back in the 80s. So this kind of particular neural network that was designed to memorize binary patterns or patterns, right, to implement some kind of memory structure that might occur in real organisms. So it's basically a neural network with D different neurons that are fully connected with each other. And the question that they are posing in a very particular sense is how many patterns can you memorize with such a network? And it's some kind of dynamical system that governs exactly what does it mean to remember or recall some pattern that you remembered. But the upshot was that that Hopfield and many other people kind of proved formally is that if you have a D neuron network, you can memorize about D binary patterns, but no more. Okay? And over the past decade, I guess people got excited about this again. I don't know the entire history, but they've been developing other kinds of biologically plausible associative memory networks. They just called them modern Hopfield networks. And these are designed in a way so that they can memorize many more patterns, let's say exponential in the number of neurons that you have. And these are still somehow like biologically plausible for some reasons I don't really understand. But the kind of connection to transformers, it turns out that the update rule in this dynamical system is exactly the self-attention mechanism that's used in transformers. And this has kind of inspired a lot of people who are interested in dynamical system to kind of extrapolate from this. What can you kind of understand about this kind of dynamics? So nice work out of MIT was looking at what happens if you look at a continuous version of these dynamics, at least at random initialization. What kinds of values did these things converge to? Some kind of clustering behavior or some collapse that happens. So this is very interesting, and I think very fruitful direction to try to understand what implications this has for what transformers can do in the context of language models. Great. Okay, any last questions? This is all I wanted to say. Somehow really the scope of this tutorial was just to give a high-level overview of what transformers do, some theoretical perspectives, but there's a lot of open questions. And I think all the details and exactly what transformers are, all these bells and whistles, and all these different perspectives, theorem people approve, it's not exactly all clear how they are essential to the functionality of language models. So I think the big question is to figure out what are the essential ingredients, and how does this let us kind of understand transformers better and produce better architectures and better language models. All right, thank you.
I just want to better understand the motivation behind the work on expressivity of transformers. Imagine if we can answer all the questions about expressivity, what is possible in designing with the specific architecture of transformers. Can we actually answer the question that why are these starting to make sense in practice, given training with data?
Yeah, so the expressivity results by themselves don't directly say anything about what you can actually express if you want to train them from data. That's a whole separate question that's not answered by that line of research. But maybe it gives some lower bounds, and like if you can't even express it, you probably can't learn it.
But the very simple idea of induction head seems very close to the simple Lenfeld-Zev compression. I mean, I guess there's more sophisticated development in both. So is there some idea or experimentation on incompressible versus compressible strings and how maybe GPT works on strings that are incompressible?
I don't know of a study, but anyone know if there's been studies? The question is have been studies about how well these models work on compressible versus incompressible sequences. I don't know.
It is work. I'm not sure if it is work comparing a study. Any learning method is also or prediction machine is also a compressor. I think there is a compression, and it is work in studying the language models as compressor and comparing them.
That people measured people measured the rate at which these models are.
And according to how, whether they provide actually compression, like how they compare to, for example, just using the very strange.
There's this challenge that I think I forget who it is that set it up, but maybe Hutter, in fact. It's a challenge to find the best possible compression of some some text he posted on the internet. And I think that the best compressors now are somehow based on some deep neural nets, maybe neural nets, I don't know, maybe transformers, LSTM. Yeah.
Yeah, I guess I don't know about just the expressive transformers, but at least for loop transformers, there are like these papers that there is at least one by Dimitris and Jason. They show
Yeah. The Tongue also has something like this.
a lot of like things that you could.
Yeah. There's definitely other ways you could use modes of operation for a transformer that are not just think of it as a circuit or think of it as a circuit plus some extra tape.
Memory and scratch pad.
Okay, well, thank Ankur and Daniel for their wonderful talk. The next talk is at 2:30, so there's still